Yeah. Yes, we are good to go. So let me share my screen. Okay, so guys, can you see my screen? Are you able to see my screen? JNV Srikakulam and other YouTube friends, please do respond in the chat box. Are you able to see my screen? Okay, so good afternoon, one and all. Today we are going to discuss about importance of the SN1 and SN2 reaction. Last time I just given the glimpse of it. So, but today we are discussing about the importance of this one, SN1 and SN2, and then we'll move to the other important, what we call topics of our concepts. Okay, so preparation of haloarenes. So basically, SN1 reaction is a substitution nucleophilic reaction for the first order. Okay, or unimolecular reaction, we can say. So it depends upon the alkyl halide, what type of alkyl halide you are having. So it is the rate is completely strictly depends upon the alkyl halide, whatever the alkyl halide we are taking. Okay, so and it will helps in the formation of carbocation. Let's suppose if you are having a compound like this A, B, Z, and X, whereas X is a living group, and if you are having any what you say that neutral nucleophile or polar protic solvent, the first step will be the nucleophile will be leave here, and you are going to form a carbocation here. So where you are going to get a carbocation here, and this particular carbocation, okay, is sp2 plain carbocation, and the second step will be the attack of nucleophile. So the second step will be the attack of nucleophile. The interesting fact is that the nucleophile can attack on the top end or it can attack from the bottom. So whenever the nucleophile can attack above the plane or below the plane, it will going to give you two products. So first is retention and another one is inversion. Okay, so I will show you those retention and inversion products. You can clearly see here. So one is retention and the another one is inversion. Okay, so we can say from here. Yeah, so we can say from here. So this is if you see this particular product. Yeah, so the living group is from the left side. Let's suppose the living group is towards the right. So if the attack of the nucleophile is towards the right, then we call it as a retention. Okay, then we call it as a retention. And if the living group is, if the attacking nucleophile is a backside, then we call it as a inversion. Then we call it as a inversion. So how much percentage this retention and inversion can take place? Both 50-50% can take place. How much? Both 50-50% it can take place. When 50-50% taking place, we call them as racemic mixture. We call them as racemic mixture. Okay, we call them as racemic mixture. So these racemic mixtures are optically inactive. Optically inactive. What is the meaning of optically inactive? Means if you pass a plain polarized light, these compounds will not rotate the plain polarized light. If they are rotating towards left, then we can call it as levorotatory. If they are towards the right, then we can call it as a dextrorotatory. Okay, so left will be levorotatory, right will be dextrorotatory. Yes, individually they will form, but we are getting a mixture of compounds. So if this mixture of compounds, if we are keeping, one will try to shift towards left, another will try to shift towards right. So both will cancel each other. So that's why the plain polarized light will not tilt. So that's why we can say that 50% of racemic, 50% of D isomer or L isomer will going to call it as a racemic mixture. So these racemic mixture are usually optically inactive. Now, formation of carbocation is taking place. So the first step is, I told you, rate determining step. In the last video we discussed, the first step is the rate determining step, whereas your rate will be depending upon this particular carbocation formation. So we can clearly say that whenever there is a carbocation is taking place, we need to talk about the stability first. We need to talk about the stability. So in order to do the stability, we will go into rearrangement, we will do ring expansion or ring contraction. So there are so many ways, okay, where the stability of carbocation can be attained. So the stability of carbocation can be explained by inductive effect, you may study. Okay, so plus I group, it is directly proportional to the plus I group. So carbocation stability is directly proportional to plus I group and inversely proportional to minus I group. So plus I group will give the electron. Already carbon with positive charge is having less electron, it will be unstable. Plus I groups are electron donating groups. So that's why they will increase the stability of carbocation. And minus I group are electron withdrawing group, they will decrease the stability of carbocation. And another one, by doing the alpha hydrogens. So if you know the alpha hydrogens, so you can also get the stability order. So more the alpha hydrogens, more will be the stability of carbocation. This is what we have learned in the previous GOC classes of class 11. So to get the carbon like stability of carbocation, we can do the rearrangement, we can do the ring expansion and everything and all. Now, stability of carbocation, I mentioned certain things here. What is B plus, A plus, 3 plus, and 2 plus, and 1 plus. Now, let me draw you something for you. Okay, let me draw you something so that it will be useful for you all. Now, so if I am, now the question is, how this SN1 reaction can be determined? So that is the biggest question, right? So SN1 कैसा determine करेंगे? Let's suppose if you are having halides like this. So CH3, CH2, X and CH3, CH, CH3, X and CH3, 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 X. So now if you see in this first, these are the compound A, compound B, and compound C. Among these three, what is the type of alkyl halide it is? What is the type of living group is there? And what are the type of reagents we are using? That is matters most. But if I am asking you in the examination, they will ask among the following ABC, which favors SN1? Okay, so among the ABC, which favors SN1 the most and the least? Like this question will ask. Or they will ask increasing order of SN1 or decreasing order of SN1. Now, we already know that SN1 will be depending upon the stability of carbocation, and I told you the stability of carbocation depending upon B plus, then A plus, then 3 plus, 2 plus, and 1 plus. What is the meaning of B plus? B plus is called as benzyl cation. What is that? Benzylic cation. What is that? Benzylic cation. Sir, can you give the structure of benzylic cation? Yes, of course. You just draw the benzene and attach one CH2 group with positive charge on it. So the sp3 carbon with attached with sp2 carbon and having a positive charge is called as benzylic cation. Now you have a doubt, sir, why this is highly stable? Why this is highly stable? The only reason because here there is a conjugation. If suppose if I'm removing the hybrid and writing the canonical structure of it, this is pi sigma positive pi, then sigma pi sigma pi sigma. So there is an extended resonance is there. So that is why benzylic cation is more stable than allylic cation. So allylic cation, how do you write the allylic cation? CH3, CH, double bond, CH and CH2, Cl. So ideally, let's suppose if I'm writing Cl here, okay, I don't know why the end is not working. Okay, so CH, CH3, CH double bond, CH, bond CH to Cl. Now this is sp2 carbon and this is sp3 carbon. Again, you can see here CH3, CH, double bond, CH2, sorry, CH, CH2, positive charge. Again, positive charge, sigma pi. So positive charge, sigma pi. Whenever if you see pi, sigma positive, pi, sigma lone pair, or pi, sigma free radical, pi, sigma pi, these kind of arrangement is called as conjugation. These type of arrangement is called as conjugation. If you see these kind of conjugation, you strictly fix in your mind that they are highly stable because of the resonance. Is it clear to you all? Clear? Yes. So now the benzylic cation is more stable than allylic, then tertiary, primary, and secondary and primary. Now, after removing these halogens from here, you are going to get positive charge on these particular carbons. You are going to get positive charge on these particular carbons. Now, the positive charge on these particular carbons, the positive charge on these particular carbons. So this is obviously this carbon is attached with one carbon. So this is primary carbocation, and this is attached with 2 carbon, secondary carbocation. This is attached with 1, 2, 3 carbon. So this is tertiary carbocation. We already know tertiary carbocation is more stable than secondary carbocation than primary. So it is very easy that if you determine the carbocation, then you can easily determine the stability of it. Then you can easily find the major product of it. Okay. So this is the order. Again, remember benzylic, allylic, tertiary, secondary, and primary are the stability of carbocation. Okay. Pretty clear, I think, for you all. Okay. Along with that, we are having JNV Mahe team joined bit late. Okay, fine, no issues. Yes. Next, we are talking about SN2 reaction. We'll see some examples of SN1 on the upcoming video. What we're going to talk about SN2 reaction. This is another big interesting fact. So SN2 is substitution, nucleophilic substitution, second order reaction. Nucleophilic substitution, second order reaction. Now, if you see this, you are having an alkyl halide, and whenever you are having any particular reagent, if I am say alcoholic KOH, if I am taking, so here the nucleophile you are going to get OH minus, which is a strong base, or we can say strong nucleophile. OH minus is a strong nucleophile. Again, remember neutral nucleophiles are there. I have a doubt that what is the meaning of a nucleophile? Nucleophile is simply nothing but an electron-rich species. What is that? Electron-rich species. Okay, so which is ready to donate its electron. Also, simultaneously, it can also act as Lewis base. Okay, it can also act as Lewis base. So nucleophile is an electron-rich species. It is ready to donate the electrons, and so it requirement of nucleus. Okay, so I can clearly say from here, red is dominating, so that's why I'm changing the color. Yeah. So now in this particular case, if I am having like this CH3, CH2, yeah, Cl is there, and now if I am having OH minus, which is a strong nucleophile, and whenever these kind of reactions are there, my rate of reaction depending upon both alkyl halide and the nucleophile. So I can clearly write that rate is directly proportional to alkyl halide and the nucleophile. Okay, I hope you guys understand. Rate is directly proportional to the alkyl halide and the nucleophile. I hope you guys are clear with this. Okay, so now the another important factor we need to remember one thing: steric hindrance. What is the meaning of steric hindrance? Steric hindrance is simply nothing but, let's suppose if you are having a group A, B, and D, and here one halogen is there. So whenever the nucleophile is trying to attack, both A, B, and D, if they are bulkier, then they will repel the nucleophile to attack. So they will hinder, they will stop the attack of the nucleophile. So obviously A, B, C should not be the bulkier groups. Sir, you are telling about bulkier groups. Sir, what is the meaning of bulkier groups? So bulkier groups are simply nothing but these ethyl, propyl, okay, or isopropyl, whatever the groups which are having more carbon chains, what they will do, they will act as a protectors to attack of the nucleophile. So obviously less steric hindrance should be there. Less steric hindrance, or we can say that less crowd. मान के चलेंगे, if you go to any particular temple during the Thursdays or Saturdays, it is huge rush. Correct. So that particular rush is a steric hindrance. So you will not able to see the god that much easily. But if you go on Sundays or if you go on normal days, the people will be not there, then you don't have that much crowd. So you will have a less steric hindrance. So crowding is steric hindrance, less crowding means less steric hindrance. So obviously for SN2, less crowding should be there. Okay. So attack will be stronger nucleophile. What are the stronger nucleophiles? OH minus or CH2 H5O minus. Ideally, sometimes it will undergo elimination also. Sometimes it will undergo elimination. We'll discuss that one later. But OH minus, CN minus, these all are stronger nucleophiles. They will undergo what? Even I minus also. Okay, I minus, these all are the stronger nucleophiles. They will undergo SN2 reaction. So now the SN2 reaction order. Now the SN2 reaction order, I'm writing here. Yeah. So now the SN2 order will be, if I'm going to take the order of SN2 reaction, will be first methyl halide. Okay, because very less crowding will be there. Then primary halide and then secondary halide. So very less crowding is there and less steric hindrance. So that is why this SN2 mechanism favors more. So that is why SN2 mechanism favors more for methyl halide. Why not tertiary halide? Why not tertiary halide? Tertiary halide will not undergo SN2 because of more steric hindrance. Now, you already know that the attack of the nucleophile is depending upon the what steric hindrance and the depending upon the nucleophile. What type of nucleophile? Whether it can replace the living group or not. So here this is acting as a living group. So this living group is going or not. So here there are some terms mentioned called R and S. What is R and what is S? Many students might have get doubt. R and S are configurations. Configurations means very simple. If I am going to tell you here, just listen. R and S, I'll give you the clarity. Let's suppose if I'm having a carbon A, B, C, and D and Z. Let's suppose like this it is there. So what is the meaning of this one? This carbon is attached to 4 different elements. 1, 2, 3, 4. These four are different. When a carbon is attached to 4 different groups, we call this particular carbon is called as chiral carbon. What we are going to call it as chiral carbon. When you are trying to keep the mirror here, you are going to get another one like this. You are going to get D, A, and B, and Z like this. So to determine these two, these are called as optical isomers. If I am calling this as R isomer and another one will be S isomer. Sir, can you help me how to find the R and S isomer? Very simple. Just draw one example I am taking. So if we are having Cl, Br, okay, iodine and hydrogen. Now if I am trying to give the priority based upon the atomic weight, priority based on atomic weight. Based on atomic weight, if I'm giving the priority, I'll take another color, guys. Yeah. So priority based upon the atomic weight, iodine will get the number 1 position because iodine have more molecular mass. Then bromine will get 2nd, chlorine will get 3rd, and then hydrogen will get 4th. Now the lowest living group, or we can say the lowest priority group, is present at the vertical line. Okay, and now you see 1, 2, 3 is there. So the rotation will be like this. 1, 2, 3. Then we can call it as a clockwise rotation. Whenever there is a clockwise rotation, it is always favors R configuration. Now, simultaneously, what is the mirror image of this one? What is the mirror image of this one? If you keep a mirror image of this one, you are going to get the product what? Cl, okay, Br, and I and H. Correct? If you give the numbering 1, 2, 3, 4. So what is the rotation here? This is anti-clockwise. So anti-clockwise, this will become S configuration. I hope you guys understand this one. Clear? So R and S configurations are very easy to determine. First, assign the atomic weight, and after assigning the atomic weight, just check whether which clockwise rotation it is. If it is a clockwise, then it will be R, anti-clockwise S. But another very, very most important, if the lowest priority group is at horizontal line, R will become S and S will become R. बस इतना याद रखो. If the lowest priority group on the horizontal line, अगर यहाँ पर है, then it will become R will become S and S will become R configuration. Okay, very, very most important. Okay, lowest priority group in horizontal line. Right. So that is what, yeah. So this is the overall conclusion of SN1 and SN2 reaction. Even though in the last video we have discussed about some points, but still I just want to give you. And here racemic mixture is possible, whereas racemic mixture is possible, whereas you are having an inversion product is possible. Whereas you have inversion product is possible. And this is a second order kinetics, and you are having a substrate and a nucleophile. Okay. Reaction proceeds in single step. It will take in two steps. One is formation of carbocation, and second one is attack of nucleophile. Okay. So here you will have an inversion. If the original product is R configuration, the product will be yes. If the reactant is S configuration, the product will be R configuration. I hope you guys understand the difference between SN1 and SN2. Now let us do some of the examples so that it will be easier for you. Okay, so that it will be easier for you. Okay, now tell me, among the following, which will undergo SN1 and SN2 faster? ठीक है ना? तो चलो, let me give some NCERT examples only. I'll see how many people are able to understand. CH2Cl, and next one is Cl. Now, among these two, if I'm asking you, among these two, which is having more SN1, which is having more SN1? So SN1 favors tertiary, secondary, and primary. Now we have to see what type of carbocation it can form. After removal of chlorine, you will get carbocation here. After removal of chlorine, you are getting carbocation here. Okay, now you can see this carbon is attached with only one carbon. This carbon is attached with only one carbon. So that's why this is primary carbocation. What about this one? This carbon is attached with 1 and 2. So then this will become what? Secondary carbocation. Okay, so primary carbocation and secondary carbocation. So secondary carbocation is more stable than the primary carbocation. So SN1 favors for the option. Let's suppose if this is A and this is B, so B is greater than A for SN1. For SN2, ulta ho jayega. Now the question here is, bromine is there. Now the question here is like whether it will go SN1 or SN2. Whether it will go SN1 or SN2. Because in SN1, tertiary, secondary, and primary. In SN2, it will be methyl halide, and primary and secondary. So secondary is favors in SN2 also, primary also. Okay, sorry, secondary is favors in SN2 also and SN1 also. So how to determine this? This is a secondary alkyl halide, means you are going to get a secondary alkyl halide, right? So this is secondary because 1 and 2 carbons are there. So this is secondary alkyl halide. So this is secondary alkyl halide. So this secondary alkyl halide is attached, means this carbon is attached with bromine. Clear? So this carbon is attached with bromine. Okay, so this is secondary alkyl halide. Sir, well, now this is secondary. Will it undergo SN1 or SN2? Question will come, yes or no? Can anyone tell me how to decide this is undergo SN1 or SN2? Tell me in the chat box, guys. Please do reply in the chat box. Whether it will go undergo SN1 or SN2. Tell me in the chat box. You can use whether it will go undergo SN1 or SN2. Tell me in the chat box. Hello, are you guys there? No one is replying, man. Why? You didn't get our what? This topic has been taught in your schools also, right? Yeah, I've got one response. SN2, JNV Mahe team telling. What about other schools, guys? Please do reply in the chat box. What about other schools? Tell me, what is the other schools? Very simple. SN1 and SN2 is depending upon the strength of the nucleophile. Strength of nucleophile. So just remember some of the nucleophiles. Usually these are polar protic solvents. That means aqueous KOH, like aqueous KOH or aqueous NaOH, okay, or moist Ag2O. Okay, so these kind of reagents are there. Usually weak nucleophiles are there. They will undergo SN1 mechanism. What about SN2? SN2 are strong nucleophiles. SN2 are strong nucleophiles. What are those? OH minus, CN minus, okay, CH2H5O minus. Okay, this is undergo elimination also, but sometimes favors SN2 and I minus. These all are the strong nucleophiles. So how to decide whether it is a strong nucleophile and weak nucleophile? Strong nucleophile will have the negative charges. Strong nucleophile will have the negative charges. And if they have given alcoholic KOH, you just simply remember this will undergo elimination. This will undergo elimination. But if they are giving like this, simply KOH is given and they have mentioned like this, then you can go to the SN2 mechanism. So now if I'm giving you OH minus, so OH minus is a strong base, so this one will become SN2. Okay. Another very, very most important you people remember, whenever you are having ethers like ROR, it is always undergo SN1, no SN2 is favors, especially tertiary mein to bilkul nahi. So always SN1 depending upon the groups attached here. So SN1 usually favors over SN2. And another very, very important, SN1 and SN2 does not observe in bicyclo, okay, and alene, okay, spiro, vinyl and phenyl halides. Sir, ये क्या है? Bicyclo क्या है? Just draw one structure here and draw one bridged carbon here. And if the halogen is attached to the bicyclo compound, it will not undergo SN1 and SN2. Even for a spiro compound also. Even for the spiro compound, let's suppose if you are having a spiro compound, which is a pentavalency, this is also not undergoing. Even for the vinyl means how it will be there? CH2 double bond, CH2 Cl. So vinyl is also not going to give the substitution reaction. Phenyl, what is phenyl? If the benzene is directly attached to the chlorine, so this is also not going to give the substitution reaction. So why they are not going to give? Because they don't have that much ability to lose the, or we can say that to undergo the substitution reaction. Bas itna hi yaad rakho. I think I have covered almost all points in a simple, brief way. Once again, pause the video, get the YouTube recording, try to answer these questions. Okay, so it will be useful for you. Okay, so very, very most important, guys. Okay, now we are studying about the preparation of haloarenes. Okay, so before going to study about that one, let me give you one homework. Okay, yeah. A, B, C, and D. So I want you to write SN1 and SN2 order. SN1 and SN2 order. This is homework. This is homework for you. Take a screenshot of it, write down in your notes, and your YouTube friends and other schools, whoever joined here, write down in your notes, try to answer the SN1 and SN2 reaction. Try to write down. Again, remember the trick. Remember the trick. Okay. Remember the trick. What is the trick, guys? SN1 favors benzyl cation, allylic cation, tertiary cation, secondary cation, primary cation, and that's it. What about SN2? SN2 favors methyl halide, primary halide, secondary halide. It will not go tertiary halide, will be not favors in SN2. but tertiary halide will with a strong base undergo elimination. So usually the reagents are aqueous KOH, H2O, usually polar protic solvents. For SN2, I minus, OH minus, CH3O minus. So strong bases or strong nucleophiles favors SN2. So based upon that, order kar dijiye. Can anyone mention the order of SN1 in the chat box? Guys, can anyone mention the order of SN1 in the chat box? Come on. Try kar lo. Try to answer in the chat box. इतने सारे स्कूल्स हैं, आंसर कर लो इसका ABCD का, विच इज प्राइम SN1 एंड SN2 ऑर्डर फाइंड कर दो. यार दिस इज द CBSE क्वेश्चन, यू हैव टू आंसर इट, यू कांट एस्केप इट. दिस इज द CBSE क्वेश्चन, यू हैव टू आंसर इट, यू कांट एस्केप. Okay, so if you are feeling shy to give the answer, it's okay, keep it with you. And exams are approaching, please, even if you're not replying for me, I know because of technicalities, might be some schools have issues, but try to have a clarity over the concepts which I was taught to you. Okay, so remember SN1, yeah, very good. JNV Mahe team given SN1 DBCA, D tertiary, yes, D is tertiary, so that's why correct. And B is secondary, very good, B is secondary. And C is primary, and A. But the point here is like key, both A and C both are primaries. But among these two, which is more stable? Among these two, which is more stable? C is more stable. Why C is more stable? The reason because here we are having 2 plus I groups. So when we are having 2 plus I groups, the C will have the more stability. Here you are having only 1 plus I group. So that's why you are having this one. And you are having 2 alpha hydrogens and here also 1 alpha hydrogen. Okay, so just remember that one. Okay, moving on, preparation of haloarenes. Very good, JNV Mahe team. Preparation of haloarenes. So now the preparation of haloarenes, basically before studying about the preparation of haloarenes, we will study about the physical properties and the chemical properties of haloarenes. First, they are physically colorless, they are stable in liquid, pleasant odor, means they will smell good, decent, right? They are usually insoluble in water but soluble in all organic solvents due to its inability to form hydrogen bond with the water. So let's suppose if I'm having a alkyl halide or aryl halide, we call them as aryl halide. What is the meaning of aryl halide? Where the benzene is attached to the halogen compound. So those are called as aryl halides. So these aryl halides are basically not soluble in the water, means they are not insoluble in water but soluble in the organic solvents. Why? Due to the inability to form hydrogen bond with the water. So water से hydrogen bond बनाना मुश्किल है, तो इसीलिए वो ऑर्गेनिक में सॉल्व होता है, इनऑर्गेनिक वाटर में सॉल्व नहीं होगा. Density usually heavier than water. पानी से ज्यादा density होगा because mass per volume of the particular haloarene will be more. So that's why density will be higher. So the density order will be, as I told you, as per mass per the volume. Iodobenzene will have more mass compare with the chlorobenzene. So that is why the density of the haloarenes favors iodobenzene, bromobenzene, and chlorobenzene. Okay. Now, boiling point is very most important point in your examination. So boiling point of aryl halides is greater than alkyl halides. What is the reason? What is the reason the boiling point of alkyl halides and aryl halides are having more? Usually in aryl halides, if you see, these are the aryl halides. Okay. So what is going to happen in this case? Means they are trying to give the electrons inside the system. That means they are acting as plus M groups and partial double bond character will be developed. So when there is a partial double bond character is developing, the bond strength of iodine and the carbon, the bond strength between iodine and carbon increases. So you require higher energy to break those bonds. So higher energy to break their bonds. And last point is isomeric dihalogens are almost same. What are the isomeric dihalogens? Cl and Cl. and you can see here Cl and Cl. So these are the dihalobenzenes, and they are isomers, and the boiling point is nearly same. Okay, but very most important in your examination point, melting point. So what will going to happen for the melting point? So the melting point is the para-halobenzene and the ortho dihalobenzene and meta-dihalobenzene order will be higher. Why para-dihalobenzene? If you see the para-dihalobenzene, here benzene, chlorine is there, chlorine is there. It can form a beautiful crystal structure. It can form a beautiful crystal structure. It can form a beautiful crystal structure. Okay, very beautiful crystal structure it can form. ये ऐसा crystal structure form करेगा. So that is why it is acting as a more like a crystal lattice, very strong crystal lattice. ये strong crystal lattice form होगा, and इसके crystal lattice का मतलब हो गया lattice energy. So you require higher lattice energy, like to break the lattice energy. Already it is forming a crystal lattice. It possesses lattice energy. So in order to break the bonds here, you have to suppress or you have to overcome the lattice energy. So that's why we can say that higher melting will be the para, then ortho and meta. Okay. Next, chemical reactions. Now we are seeing about the chemical reactions. So basically chemical reactions are of two types, nucleophilic and electrophilic. So basically what are nucleophilic substitution reactions? Just now we have seen SN1 and SN2. Okay, so these are the nucleophilic substitution reaction. Electrophilic substitution reaction kya hoga? When you are having an electrophile, it can try to attack on the particular ring. Okay, so now we just see from here, right? First, we will talk about the nucleophilic substitution. So I'm so sorry. Just a minute. Yeah, now you can see the nucleophilic substitution is usually less favors. Why the reason? Because what might be the reason? So there might be n reasons will be there. Okay, so one of the reason here is like, oh, just a minute. So the reason will become, you can see here, chlorine is acting as a plus M group. Sir, what is the meaning of a plus M group? Plus M groups will donate the electrons, into the system. The plus M groups will donate the electrons into the system. When they are donating, you are having a partial double bond character and you are getting positive charge. So due to the partial double bond character, it is very difficult to break. So the bond cleavage of haloarene is very difficult. So that is why aryl halides are poor. Where aryl halides are poor towards substitution reaction. Okay, aryl halides are poor towards the nucleophilic substitution reaction. I hope you guys understand why they are poor to the nucleophilic substitution, because of the partial double bond character. They are unable to break the bonds between the chlorine and the carbon. Next, the difference in hybridization of atom in CX bond. So the carbon attached to the halogen is sp2 hybridized, while in case of haloalkane it is sp3. So you can see here we are having sp3, here we are having sp2. So sp2 hybridized carbon is having more percentage of S character, and we can also say that it will be more electronegative. Okay, so when this is more electronegative, compared to the sp3, it can hold the CX bond more tightly than sp3. Means दूसरा reason क्या हो सकता है? यहाँ जो halogen, I'm extremely sorry guys. So the next thing is like the halogen and the carbon. The halogen and carbon, this is sp2 hybridized carbon, which is having 66% of S character, which is favors for the more electronegativity. So when there is more favoring of electronegativity, what will going to happen? They try to pull the electrons to itself. So then they will tightly have a bond between carbon and halogen. So then they will unable to release the halogen from there. So that's why Usually alkyl halides are more reactive, or we can say towards nucleophilic substitution compared to aryl halides. So this is what you people need to remember. So that's why shorter the bond length, then the longer bond, so less will be the reactive. Okay, so usually these are the some stability, some of the reasons. Next one, instability of phenyl cation. So if you see, I already told you last time, whenever you are in chlorine, for trying to remove the chlorine, you are going to get what? Positive charge on the benzene. Remember guys, positive charge on benzene is highly unstable, because we can clearly say here these electrons involving in conjugation. Okay, so that is why this will not undergo as nucleophilic substitution reaction. So phenyl cation formed as a result of self ionization, not stabilized by resonance. Self ionization, वो self अंदर ही ionization होती है, वहाँ resonance will not be takes place. So that is why phenyl cation is unstable for the nucleophile attack. Okay, so the reason also I mentioned, because of the possible electron repulsion, it less likely for an electron rich nucleophile to approach. What we are talking about, why the nucleophilic attack, or we can say the reactions are poor in aryl halides. Aryl halides, why they are poor? One reason, they are getting partial double bond character. Second, sp2 hybridized you are getting, and third, self ionization of phenyl. These are the some of the reasons for not favoring nucleophilic substitution reaction, but they will favor for the but still there are some of the compounds which can favor nucleophilic substitution reaction. Okay, guys, last 5 minutes. There are some of the reactions which we can see in our examination, that is preparation of phenol from alkyl. Aryl chloride say phenyl, aryl chloride say phenol, not phenyl, phenol, by using a Dow's process. So in Dow's process, what is going to happen? Nucleophilic substitution of chlorine by the hydroxyl group. So OH group will be substituted by, Cl will be substituted by OH group. I hope you guys are clear. So the temperature has to be noted, because if based upon the temperatures only you'll get the products. Okay, so ये बहुत ज़्यादा important है, इसको याद रख लेना, ठीक है? So now you can see the presence of an Le electron withdrawing group NO2 at ortho or para positions increase the reactivity of haloarenes. Yes, obviously what they will do, the -I groups are usually electron withdrawing groups. They will pull the electrons downwards, so then chlorine can release very easily. Why the presence of +I or -I favors more? Because they will pull the electron downwards, then chlorine can leave. Okay, when chlorine can leave, then we can clearly say from here the stability of carbocation is there. You can see here, when we are having one NO2 group, means -1I group, the temperature is 443. When we are having two NO2 groups, the temperature has been decreased to 368. When we are having three, then there is no temperature is required. Warm conditions maybe it can convert. So the name of this compound is what? Called as what? Can anyone tell me? Picric acid. What we are going to call it as? Picric acid. Okay, so the name of the compounds we can tell this is picric acid. I hope you guys all are clear with what I'm saying. Right. So usually presence of -I groups will increase the nucleophilic substitution. The reason, because they will decrease the bond strength between the chlorine and the carbon. Okay. Yes. Electrophilic substitution. Basically, we are having 4 types of electrophilic substitution. One is halogenation. Halogenation, you can clearly say FeX3, that is FeCl3 or FeBr3, whatever the reagents may be. Okay, in the presence of FeCl3 of anhydrous medium, you are going to get a substitution. Here you are going to get Cl plus radical, sorry, Cl plus cation. This is acting as a electrophile. This is acting as a electrophile. Okay, so Cl plus radical is acting as an electrophile. So that is substituted at the ortho position and the para position. Again, why it is major and why it is minor, sorry, why it is minor and why it is major, same, due to the symmetry is one reason. And we can also say, if the chlorine, chlorine, two similar elements are near, we will observe van der Waal repulsion. Van der Waal repulsion. So that is why the distance should be more. So ideally para will be greater than meta than ortho. Why? Because of repulsions between the identical elements. Okay. I hope you guys are clear with what I'm saying. Clear? Next, nitration. So nitration also here you are going to get NO2 plus as an electrophile. This can attack at ortho position and para position. Again, para is favors more. The reason distance is higher, and also there is a bond formation, or we can also say there is a repulsion between these two, which makes the compound unstable. So para isomer, para compounds are usually highly stable. Okay. Next, sulfonation. Again, same story with the sulfonation H2SO4. We are using H2SO4. We are going to produce sulfonyl aryl chloride, and here para. So para is more stable. Again, same story. Okay, repulsions is the concern. Next one is free radical alkylation, free radical acylation. So what is free radical alkylation? Free radical alkylation hota kya hai? Free radical alkylation is simply addition of an alkyl group in the presence of anhydrous AlCl2. So first step, what is going to happen? CH3Cl, it is going to break as CH3Cl plus AlCl3, and now it will become AlCl4, okay, plus AlCl4 plus CH3 minus. So this is going to happen, and these AlCl3 and not CH3 minus exactly, it will get a partially negative charge. Okay, and just a minute, what is going to happen? Yeah, so here this particular group, okay, again AlCl3 with CHCl3, this CH3 will undergo as a product in CH3 and H at ortho and at the para positions. So this CH3 is attached at the ortho and para position, but still para is more stable because of lower repulsions. Next, Friedel-Crafts acylation. Friedel-Crafts acylation, we are using acyl chlorides. What are those? Methyl chloride is there. Ethanyl chloride is there. So ethanyl chloride, we can see that CH3 C double bond O minus, and here if you are going to get plus charge, and this will act as electrophile, and this electrophile will attack at ortho and para positions. But simultaneously I told para positions favors major because of good electron pooling and less repulsion. Okay, yeah, reaction with a metal, Wurtz reaction and Wurtz-Fittig reaction. Simple है. Wurtz reaction क्या है? Rx 2 moles लेना है. अगर आप सोडियम के साथ कर रहे तो Rx ले लो, और यहाँ से अगर आप लोग सोडियम ले रहा है तो 2 moles ले रहे हैं, so then they both will give as 2 NaCl, and RR मिलके क्या बनेगा? R. Okay, so ideally whenever we are reacting a metal, this will help in formation of alkanes. So alkanes formation के लिए ये help करेगा. Then Wurtz-Fittig reaction is there. What is Wurtz-Fittig reaction? Alkyl halide and aryl halide react with each other. मान लो ये एक alkyl halide है and you are having an aryl halide. Okay, but you want to give the product. So now the ultimately you are going to get R like this. Okay, so this both living groups will go. So how this product is attained? This product is attained by the Wurtz-Fittig reaction. Again, Wurtz-Fittig reaction, just now I told this is Fittig reaction. So these are the some examples. Okay, so these are the some of the examples. Just now I told this is Wurtz-Fittig reaction, this is Fittig reaction. Okay, that's it guys. Thank you so much for joining the class. We have finished the haloalkanes and haloarenes. Try to do as much as possible in your NCERT. Any doubts you can contact in the next class.